Yep, I'd like to first thank the organizers for making this conference happen. So I understand it has been very difficult to organize this meeting. I mean, it has been postponed a couple of times and things like that. So I greatly appreciate this. Okay, so today I'd like to talk about this, what we call fractonic phases in frustrated magnet. So first thing I'd like to do is introduce what fracton phases are. Okay, some brief introduction to fracton phases. So we have this expanding landscape of topological phases of matter. So for example, there are all these famous symmetry protected topological phases. The most famous example is a spin one Heisenberg chain in one dimension. Then we know that the ground state is ordained phase. So this is an example of symmetry protected interacting system. Then there's this popular area of band topology. And at the same time, we have this long range entangled state, like fractional quantum Hall state or quantum spin liquid state. So quantum spin liquid states are of course, important subject in frustrated magnet. Now we have relatively new phases, at least in theory land. So these are fracton phases. This is basically a new kid in town. So as you know, new kids always get a lot of attention, at least from theorists at the moment. It turns out that these phases depends on not just topology, but also the geometry of the lattice. So it's kind of interesting. So it's not a pure topological phase, but it has some aspects to it. And these phases are suggested as an error correcting code. And the reason for that is that we'll see later the ground state degeneracy of these phases is basically massive, even though these are quantum phases of matter. Also, there have been a lot of activities in quantum field theory literature because since these properties of these phases depends on not just topology, but also geometry of the system, you have to worry about both long wavelength properties of these phases, but also you have to worry about the short distance physics. So you have to somehow marry the UV limit and IR limit. So there has been a subject of active study. And these phases are also proposed for a possible quantum glass state. So these are the motivation to think about these phases of matter. So in fact, there are some exactly solvable models for these phases. But before we talk about this, one interesting thing about these phases is that the quasi particles in fracton phases have very weird properties. They have what we call restricted mobility. For example, there are particles that can only move along one-dimensional space, even though the system is defined in 3 dimensions. Also, you may have these excitations at the corners of the membrane-like object, and you cannot create these particles separately. You always have to create them as a cluster, and you can expand this membrane-like object so that the distance between these particles can be larger and larger, but again, you cannot just move one particle at a time. And more complex models, these corner excitations are defined at the corners of some kind of a fractal object, and these particles are called fracton. So as I said, there are exactly solvable models, and these are what we call commuting projector models. It's a bit like a quantum diode model, if you're familiar with those. So these models carry names like X cube, Haas code, and Shamong's code. And the most, the simplest model perhaps is the X cube model. So the model is very simple. The model is defined on the 3-dimensional cubic lattice. And there are 4 terms in your Hamiltonian. So the first term, for example, you take like a YZ plane in a three-dimensional space. And then at each link of the lattice, the XY, the YZ plane, you place a Z component of Pauli metric. So if you like, I have a product of 4 Z component of spin operators. And you can do the same for like XG plane, XY plane. So there are 3 kinds of a 4-spin interaction term like that. But then on the Q, you have you place the X component of spin operator. So there are 12 of them. So you basically make a product of these 12 X component of spin operator, and that's it. And that's basically another interaction. So you see that this is a very complex spin Hamiltonian. If you think about it this way, because there are 4 spin interactions, then there are 12 spin interactions. It's very unrealistic. But what happens is that all of these terms commute with each other. That's why it's called commuting projector model. If you do so, then the ground state is obviously given by the state that gives you eigenvalue +1 for every operator like this. So the ground state condition is very simple. That's the way that you minimize the Hamiltonian. It's just that if you do so, then you create a massive degeneracy that I will talk about later. So again, to iterate the properties of this space, if you start from a ground state, then if you apply, say, Pauli Z or Z component of spin operators at each link of this membrane-like object like that, then you can show that the cube operator gives you eigenvalue -1. So there are 4 corners that gives you eigenvalue -1. So obviously you are getting out of the ground state manifold, and that way you can create an excitation. But these excitations cannot be separated from each other. If you apply, say, sigma X operator along this chain, then again, you can create this what we call a line that can only move along 1 dimension. If you create 2 excitations like this together, then it turns out you can move along some 2-dimensional plane. So these particles are sometimes called planions. And you can also create dipoles of lions. So then you can make a corner like this. So individual particles can only move along 1 dimension. But if you make a dipole, then you can take a corner. So you can move around in the plane. So these particles have very weird properties. But most importantly, if you look at the ground state degeneracy, that's so extensive. And it depends on the geometry of the lattice system. So for example, if you take an XQ model, the logarithm of ground state degeneracy is actually proportional to the perimeter of your system. So you see this model has received a lot of attention from quantum information community because of this massive degeneracy. So a lot of people thought that this may be a good place to store a lot of quantum information. So actually these pages are proposed as a good platform for quantum memory. So again, as I said, they have a lot of activities in trying to construct quantum field theory for this. And I'm not going to talk about this today. There's also a relation to elasticity theory. It's mostly done by Leo Lajovsky and collaborators. Basically, you try to map this elasticity theory to a fractal model. Then it turns out that topological defects and elasticity theory corresponds to this fracton object. Another connection is to rank 2 tensor gauge theory, and this is the connection that this is the thing that I like to elaborate more the rest of the talk. Okay. So we are, of course, very familiar with the usual electromagnetism. And this is what we call rank 1 U1 gauge theory. So for example, we have this Gauss law, divergence equals to 0. If you violate that, then we get a Poisson's equation. And we are also familiar with this gauge transformation related to that. Rank 2 theory is just simply a generalization the familiar electromagnetism. So, now electric field, in the rank 1 theory, electric field is a vector. But imagine that now we define a tensorial electric field. So now electric field carries two indices, I and j. Then there are two different ways that we can define a Gauss law constraint. So either we use a double derivative to define a Gauss law, or we can just use a one derivative, just like what we did for the vector gauge theory. Then, of course, we can also write down the corresponding Poisson's equation. The difference here is that if you use a double derivative like this, then the right-hand side of the Poisson's equation has to be scalar. So we are dealing with the scalar charge theory. But if you use only one derivative like that, then right-hand side has to become a vector. So it turns out in this case, the charge degree of freedom is represented by some kind of vectorial charge. And there are corresponding gauge transformation. So this is very formal, but these theories already have some interesting properties that resemble the motion of quasi-particles in fractal theory that I just talked about. So for example, let's take this scalar charge Gauss law, if you like, the rank 2 Yuan gauge theory with a scalar charge. Then it turns out that
Young Baek, there's a question in the audience.
Sure, go ahead.
Carlo will ask.
I would like to ask, I mean, sometimes you write the indices, I mean, you use, upper indices or lower indices in the EIG.
Yeah, it's not important. It's not important for this theory at this point. Yeah, I'm not going to distinguish upper indices and lower indices here.
Okay, thank you.
Yeah. I mean, we are on the flat space here, so actually it turns out, I mean, for this particular case, it's not important. Yeah. Sorry for the confusion. Okay, so important thing about this Gauss law is that now we have two conservation laws, right? So usually in the usual electromagnetism, we have a conservation of charge. But it turns out that in this theory, you also have to conserve dipole moment, and that's basically the main difference. So what that means is that the typical charge configuration is like quadrupolar configuration like this. In this case, total charge is 0. The dipole moment is also 0. So now if you start from a configuration like this, in order to conserve both total charge and dipole moment, you have to move your charges in such a way that both quantities are basically conserved. For example, if you start from here, I can place charges like this. I can create some charges or create some plus minus charges, but I can only do so by conserving both total charge and dipole moment. So in that sense, motion of charges are restricted. For the vector charges.
Sorry, quick question.
Yeah.
So it seems like from the way you write it down at the top of the slide that this conservation of dipole moment and charge comes from the fact that there's no charge to begin this with, but this is not correct, right? So so even if you have charge excitations, you will still have this conservation law. So on the right hand side.
That's right. So you can start with some finite charge, right? Mm-hmm. So that you start from some actual excitations. It's okay as long as you satisfy, as long as you conserve total charge and total dipole moment, that's also fine. So this is an example where specifically total charge is 0, but of course you can have a finite total charge. It's just that you don't want to change the total charge. That's it.
Mm-hmm. So in that case, the integral is. So the integral gives you some boundary terms which
that's correct. Yes.
Okay, thank you.
Yeah, but you still have a two conservation law. That's what I wanted to emphasize. Okay, now for the vector theory, again, a total vector charge has to be conserved. Then it turns out that basically x cross rho, that object also has to be conserved. So if you think about this as a momentum, this is like angular momentum, even though I'm not the rho is not really momentum is a charge vector, but that's the analogy. So because of this, the charge is restricted to move along charge vector direction. So in that sense, the motion of charges are again restricted. So there are some relation between the quasi-particles in the fraction state and the rank 2 gauge theory. And there have been a lot of activities in the field theory literature, how to connect to these two areas. Okay, so having said that, what the aim of this talk is to find the realistic spin model for this kind of phases. So, we have seen this exactly Subhro models obviously is a very unrealistic model. It's not possible to realize such an interaction in any magnet. So I like to see whether we can make a progress for realistic models. So to do so, I'm gonna piggyback on two ideas. So the one idea we have is a quantum spin ice, and we know that quantum spin ice basically gives us the usual Yuan gauge theory, the rank 1 theory. So I'm going to give you a very brief introduction to this. I know all of you are familiar with that, but it will be useful to recall what happened there. Then I'm going to also use the idea proposed by Nick Shannon's group at IIST, and they proposed a spin model for rank 2 Yuan gauge theory in the classical limit. Okay. So basically what I'm going to do is to find the corresponding quantum model for that. So that's basically the outline. Okay, so we are all familiar with this quantum spin ice. We start from Ising model on the particle lattice, and we can write this model in terms of like a cluster spin on each tetrahedron. So the classical spin ice manifold is defined by setting this cluster spin to be 0. So we have a 2 into our configuration for a tetrahedron. Then we introduce this transverse spin exchange interaction. So that basically generates a quantum dynamics. And in the limit that the Ising coupling is much larger than transverse coupling, we can do a degenerate perturbation theory. Then we immediately generate this ring exchange interaction around the hexagon in the particle lattice. So and if you do so, then we have this famous mapping between Z component of spin to an electric field, the raging operator of spin to e to the I vector potential. So the famous relation between SZ, commutation relation between SZ and S plus immediately translate into a canonical commutation relation between vector potential and electric field. So that's the way that we can map, for example, this ring exchange term to cosine of curl of A. By doing so, we have electromagnetic action or Hamiltonian on the lattice. So we have this electric field square term, and then there's a cosine curl of A term. This is a lattice Yuan gauge theory. And in the if you are in a deconfined phase of this theory, namely in the spin liquid state, a spin I state, then you can expand this cosine curl of A, and then you get curl of A square, and that's basically magnetic field square term. So we end up with the Hamiltonian, the sum of E square plus B square, and that's the way that we recover the usual electromagnetic theory. So this is the story about Yuan gauge theory, the usual Yuan gauge theory, or rank 1 Yuan gauge theory. So Bruce will talk about this candidate material for this kind of state. Now the question is, can we generalize this to rank 2 theory or the fracton theory? That's basically the topic. So this this is what I'm going to talk about. Okay. So so what is the useful setting that we can think about? So let's think about this so-called breathing particle lattice. So in this case, say A tetrahedron and B tetrahedron sizes are very different. Imagine that. So then spin exchange interactions are going to be different on A and B tetrahedron. And imagine that the exchange interaction on the B tetrahedron is order of magnitude smaller than the interaction on the A tetrahedron. So there's some material like this. So this is the picture of this breathing particle lattice. In order to save space, I like to represent this up tetrahedron by a green dot here, and the down tetrahedron by a yellow dot here. And as you know, A and B sublattices make FCC lattices respectively. Okay, so I'm going to use this shorthand figure notation. Okay, so let's think about a very generic nearest neighbor spin interaction. So this is basically the most generic model. So we can have a Heisenberg interaction on A and B tetrahedron, and we can have Zalotchinsky-Moria. We can also allow a Kitaev interaction, and then there are also what we call symmetric anisotropic exchange interactions. So you are familiar with this Kitaev and gamma interactions from all these discussions about Kitaev model, K gamma model, and things like that. So it has been very popular, but these terms also exist on the particle lattice. Okay, so now I'm going to assume the interactions on the B tetrahedron is much smaller than those on the A tetrahedron. I'm also going to assume that Heisenberg interaction dominates over other anisotropic interactions. So these are very reasonable assumptions. So instead of dealing with this complex spin exchange Hamiltonian, it turns out it's much more useful to represent the spin model using normal mode of tetrahedron. So here, this MA and MB are normal mode degree of freedom defined in terms of like 4 spins on the tetrahedron. So each mode is some linear combination of 4 spins at 4 sides on each tetrahedron. And we can classify this normal mode using the irreducible representation of tetrahedral group. So there are 5 irreducible representations. So there are 8, I just want to remind you that A means there are only 1 mode, E means there are 2 degenerate modes, T means there are triply degenerate modes. So there are 1, 2, 3, 3, 3 normal mode for each tetrahedron. Okay. So if you do so, then you can represent the entire Hamiltonian this way, and then you can identify all these coefficients in terms of the parameters of the very general model that I wrote down. And so you can think of this A coefficient as a mass term or interaction coefficient. This really just represents the energy cost to excite this particular normal mode. So this representation turns out to be very useful. And again, I'm going to assume that Heisenberg interaction dominates. If you do so, then it turns out that the heaviest mode, or the mode that costs the highest energy, is what we call a T1 plus mode. It's because this is always the largest number. So what we are going to do is I'm going to get rid of this, because when you go to low energy limit, we are not going to excite this mode. So if I restrict to the low energy system, then we can just set those modes to be 0. Okay. So now it turns out imposing this constraint basically generates a lot, interesting constraint on the normal mode behavior on the A tetrahedron. So if you get rid of this mode, the B tetrahedron, for example, because of the fact that all these spins are basically shared between A tetrahedron and B tetrahedron, by the time you impose this constraint, you immediately generate some relation between normal mode degree of freedom on these four A tetrahedron. So if you work it out on the lattice, then obviously it involves some gradient operator between this normal mode of 4 tetrahedron, because these modes are related to each other. So it looks complicated, but you can work out that condition. So then you have some equations for that, basically relation between all this normal mode among 4 tetrahedron. And then this relation can be nicely written as some kind of Gauss law. And this is basically the main finding of this paper by Nick Shannon's group. And so, okay, sorry for that. So basically, you can define rank 2 electric field, there is a symmetric traceless part of the rank 2 electric field tensor like this. And then there's the anti-symmetric piece, and there's a part that gives you a finite trace. So this is the most general rank 2 tensor you can define. But the point is that these electric field variables are defined in terms of those all of those normal modes. So so you can think of this as a rank 2 electric field, and you see that it immediately gives you this Gauss law constraint for the rank 2 electric field. So this is nice. The cursor is now okay. So but then another thing you can do is you can go to some rather special limit. Imagine that the E mode and T1 minus mode are degenerate, but all other modes are actually the higher energy. So then what we do is in this low energy manifold, we can set all other modes to be 0 essentially, so that we only keep E mode and T1 minus mode. If you do so, the remaining electric field are just symmetric and traceless. You only keep E mode here and T1 minus mode here. All other modes are set to 0. And this theory is particularly nice in the sense that all these electric fields are symmetric and traceless. So your Hamiltonian, if you like, reduces to with this very nice form. It's basically E squared term in your Hamiltonian. And this theory is traceless and symmetric. So you end up with traceless symmetric tensor gauge theory. So this is the reason why this is nice. Is because first of all, you can reach this limit very naturally if you just set all the K-type and gamma interaction to be 0. So if you only keep Heisenberg and Zalotchinsky-Moria, you immediately arrive at this condition. So it's a very natural limit. Another nice thing is that actually we did this calculation. We did dynamical spin structure factor calculation for this classical model. So still classical, right? So it turns out that if you look at the polarized neutron scattering, and if you're looking at the spin flip scattering, then you have this 4-point pinch point in the low energy limit. So this was also discussed for equal time correlator in this paper, but we also looked at dynamical correlator, and you can see that the spin flip scattering structure factor has this characteristic 4-fold pinch point, in contrast to the usual 2-fold pinch point in the spin-I system. So there are some distinct signatures in the neutron scattering in principle. Okay, so moving to quantum theory. So we wanted to generalize this to a quantum system. But then you immediately encounter a lot of difficulties here. So for example, remember that these normal mode variables are essentially spin variables. So your electric field E are basically non-commuting field, because electric fields are basically spin, and those different component of spin, they don't commute. So if you try to quantize this theory, then you end up with some kind of non-commutative quantum field theory. So it's very hard to make a progress. So we decided to look at a different limit. So, so we like to look at this particular limit. Say here we only keep A mode and E mode, and all other T mode we say if they are in high energy mode. So we set all of these modes to be 0. We only keep A mode and E mode. So there are, one E mode and one A mode and 2 E mode. Remember that. So if you do so, then it amounts to keeping only the diagonal component of the symmetric part of the electric field tensor, and then we keep actually the trace fold part, but we ignore the anti-symmetric piece. So my electric field still a rank 2 tensor, but now it's symmetric, it's diagonal, and traceable. So it's somewhat different theory, but nonetheless, it's still legitimate rank 2 gauge theory. And it turns out we can actually solve this quantum model. And also this can be achieved by choosing some finite type interaction and the gamma interaction. So in this case, it turns out we have to keep all of the Heisenberg-Zieloczynski-Moria type and gamma interaction all together, but there are some genetic conditions that we can impose, then we can reach this limit. So it's it's still a realistic two-spin exchange Hamiltonian. Okay. So now we can work with this model. As I said, we have a symmetric piece, and there's some finite trace path, and we have this Gauss law constraint, and this is going to be very important. Essentially, all the physics comes from this Gauss law. So we only keep A mode and the E mode. So Hamiltonian is just some of these two normal mode terms. Also, we should not forget that there is a residual interaction on the B tetrahedron, and this interaction is going to be a perturbation to this Hamiltonian on the L tetrahedron. But in this a simple limit, the model turns out to be very simple. Namely, since this electric field is now diagonal, if you sum this up, it turns out that that just sum of scales of the diagonal component of the electric field tensor. And then you can think of this as the x, y, z component of some vector, EA. So the entire model just becomes some electric field scale term. And if you remember that these electric fields are nothing but spin variable, it's natural to expect that these electric field operators are variable. Actually, they satisfy the usual SU2 commutation relation. If you think about this as an x, y, z component of some kind of spin, then it's easy to understand. It just becomes a rotor model. Then and this is a very simple model. But the important thing is that all the difficulties now come from this Gauss law constraint. It's not a simple rotor model. The rotor model supplemented by this Gauss law constraint. Okay, so this is just like this commutation relation is just like a SQ and SZ operator. So you can actually label the manifold of grounds using these quantum numbers. So these are the eigenvalues of these operators. Okay? And in this case, for each tetrahedron, we know that the ground state is 5-fold degenerate with S equal 2. So in fact, this electric field, G component of electric field, can have only discrete values. And these are just all S equal 2 state at the level of each tetrahedron. But then we have to arrange these quantum numbers on the entire breeding power of Polaris in such a way that Gauss law constraint that I talked about is satisfied. So, okay, so the ground state manifold of the network of L tetrahedron is described by the
Young Baek, there's a question in the audience.
Sure.
Sorry, maybe I was not careful. So I understand that these E and A and so on, they are linear combination of spin operators. Is that right?
That's correct.
Right. And then in addition, you assume that you have a Hilbert space. I mean, that there are some spin 1/2 or maybe spin 1. Since you are talking about the spin 2 states, at least the spins on the sides of the tetrahedra must be larger than 1/2. So this
So actually, in our quantum model, we are assuming that the spin is we are dealing with a spin half system. Then when I talk of S2, this is really the spin state on each tetrahedron. So I'm talking about the ground state on each tetrahedron. So we are talking about the 4 spin. And it turns out that for each tetrahedron, the ground state is S equal 2 multiplied.
Okay.
If we start from a spin half system on a tetrahedron.
Like 16, and out of those 16, 2 to the 4.
That's correct. That's correct. Yeah, out of this 16 state.
Right.
And the ground state is 5-fold degenerate. And then so then we can just restrict ourselves to this S equal 2 manifold. So that's what we are going to do.
Right, but this S equal 2 states, these are not. I mean, from 4 spin 1/2, you can't make spin 2. So it must be that it is kind of some linear. degeneracy between the multiplets of the spin-1 objects. So it would be like 3/2 plus, I don't know. I mean, it's very weird, this S=2. Because I mean, you would also assume that you have Kramers degenerates, and you would expect the ground state manifold to have big Kramers degenerate that is even number of states, and here you have 5.
I think okay, maybe we can go back to this later, but for what I'm assuming is that for each tetrahedron, basically the electric field variable can only have these 5 different values, because this basically makes the lowest energy state at each tetrahedral level. Then if you think about the entire particle lattice, then we have to place this electric field variable on each 8 tetrahedron, and I have to tile this entire lattice. So I have to put I have to put this electric field value. One of those values have to be placed in each tetrahedron. Then I have to tile entire lattice in such a way that Gauss law constraint is satisfied. So it turns out that basically makes up the ground state manifold. Maybe we can discuss this later. I think unfortunately I don't have much time, so okay, sorry for that. Yeah, we can go back to this later, but I like to continue. Okay, so so the question is, how can you satisfy the Gauss law constraint? And it turns out that we end up with massive ground state degeneracy. So if you relax the Gauss law constraint, then you can show that the location of the excitation, if you like, what we call electric charges, these are on the p tetrahedron center. So my electric fields are defined at 8 tetrahedron. Remember that this green does the 8 tetrahedron, the yellow does p tetrahedron. So this is nothing but the Poisson's equation. So you can define x, y, z component of the vector charges, if you like, as some combination of electric field at this 4 location of a tetrahedron. So this is the Poisson's equation, if you like. And if you set all the charges to be 0, then that basically gives you the Gauss law constraint. And this vector charge is also satisfying the usual SU2 commutation relation. Okay. So then you can also define raising and lowering operators using this. So using this electric field variable or operators, you can increase or decrease your vector charges at the p tetrahedral center. And important thing is that if you write the Hamiltonian on the p tetrahedron as a perturbation, then you can re-express this Hamiltonian in terms of variables on a tetrahedron. So it turns out this generates a quantum dynamics. For example, look at this E plus E minus term. This is like a S plus S minus term in the quantum spin ice problem. So this, for example, represents the raising and lowering operator on nearby a tetrahedron. So if I apply raising operator on this a tetrahedron, then I have to apply lowering operator on the other tetrahedron. Okay, sorry. Yeah, so we apply E plus here, E minus here at different location of a tetrahedron. So pictorially, the process looks like this. So if you start from some background charge configuration, it means some background electric field configuration. So here I can start with some uniform background. Then if you apply a raising operator on one location of the tetrahedron, it turns out that you will create this quadrupolar-like configuration on the b tetrahedron center. And if you apply E plus and E minus at nearby a tetrahedron location, then by creating this overlapping quadrupolar configuration of charges, you basically cancel the excitation in the middle. And if you keep doing that, if you keep applying raising lowering operators, then you keep canceling the charges at the center. So basically, you keep creating more charges at the boundary, but the central part basically becomes void. And you keep doing that, then you end up with some kind of membrane-like object where you only create excitation at the boundary of this, and in the center of the membrane, basically there's no excitation. And this is basically happening in a two-dimensional plane. Okay. So now when you push all of these charges to the boundary, and if you apply a periodic boundary condition, it turns out you can cancel all of these charges. And after that, what actually happens is that the system goes to one member of a degenerate manifold. So if you start from one charge configuration, so electric field configuration, and by creating charges and annihilate them using boundary condition, so you're not going back to the original configuration, but you are going to one configuration that belongs to this massive degenerate manifold. So it's very similar to quantum spin ice problem. And we can keep doing this to generate all the degenerate ground state. And this is similar to quantum Hall state or quantum spin ice state, where you can move around your quasi-particles and annihilate them, then you can go to another member of the degenerate ground state. Okay. So it turns out that if you count the ground state degeneracy of this model, we couldn't find the analytical formula. So we just used the computer to count it. So we don't have a closed formula for this. But what's interesting is that indeed the ground state degeneracy depends on the lattice geometry. So for example, here I'm showing you some unit of up tetrahedron and down tetrahedron. Remember that these greens are up tetrahedron, these yellows are down tetrahedron. So when I said 111, Lx, Ly, Lz equals to 111, I'm talking about this unit. And then, for example, with this unit, the ground state degeneracy is 85. But now you can keep increasing the system size. You can change the system size. And you can have all kinds of degeneracy. What is interesting is that ground state degeneracy is different for the same volume of perimeter. So, these two geometry have the same perimeter, but the ground state degeneracy is different. The same volume, the ground state degeneracy is different because the perimeter is different. For a fixed perimeter, the larger volume gives you actually smaller ground state degeneracy. For a fixed volume, larger perimeter gives larger ground state degeneracy. So it's very hard to figure out the rules, but what we can say is that for the one-dimensional geometry, ground state degeneracy monotonically increases system size. But in all other cases, ground state degeneracy does not monotonically increase with the volume of perimeter. And ground state degeneracy is larger for larger perimeters for a given volume. And we can sort of qualitatively understand this because the number of times that membrane operators can be applied depends on the number of planes, it turns out. And for FCC lattice, there are 2Li number of planes in each I direction. So the total number of planes is this. And so that's why ground state degeneracy becomes larger, because I can create more membrane operator like this that I described to you. For a given perimeter, larger volume gives you smaller ground state degeneracy because number of constraints increases the volume. So since your number of constraints increasing, the ground state degeneracy turns out to be smaller. Okay. So at the end of the day, the point is that the ground state degeneracy is non-extensive with the volume, and it actually depends on the geometry. Okay. Another interesting thing is that I think I'm going to be very brief here. So what about magnetic field? We only talk about the
Just Yongbek, we are -4 of your time.
Okay.
Maybe can you
wrap up.
back up the end rapidly?
I'm gonna wrap up this. So okay, so the point is that we have we constructed a realistic two-spin exchange Hamiltonian on this breeding paracollars, and we showed that there are all these gap charge excitations, that can only arise as a cluster. And then we found that just like other fractal models, the ground state degeneracy depends on the lattice geometry. So in a way, this is a realistic model for a fractal quantum phases. All right, thank you very much.
Thank you very much, Yong Kim. So we have time maybe for short questions.
Hi, Yongbek. I had this question, I mean, sort of related to Carlo's question, but
Yeah.
so in the usual U1 gauge theory, one way that the system remembers that it's a spin half is because of this background electric field. But so you think that this rank 2 gauge theory completely forgets about the spin halfness of the system, apart from the fact that you get these 5-fold degeneracy?
I think there must be a way that the rank 2 theory remembers the background charge configuration. I haven't thought about that, but I think that depends on the spin model. So for this particular model that I talked about, the back, you can only have certain kinds of background charge configuration, right? So that restriction really comes from the microscopic model. The same is true for the quantum spin ice model, right? Depending on whether you start from say 0 flux state or pi flux state. There are different constraints on the background charge configuration. So here, I think that the same applies. I didn't investigate like if I change my models, then how that depends on the background charge configuration. I didn't investigate that, but that question will be important to answer questions like whether we are really in the deconfined phase of this gauge theory or not, things like that. But I didn't look at those details. Yeah, maybe there is a way to formulate this to see where this information that the underlying spins have spin half quantum numbers.
Okay. Are there any other urgent question, maybe online? No? Okay. So if no, let's thank Yongbek again. And
Thank you very much.
thank you.